Okay, welcome everyone. Today we have one of our own, Serina Chang, who is a new professor here in EECS. She has a PhD from Stanford, for which she actually won the KDD Best Dissertation Award. She works on AI and human behavior, particularly concentrated on healthcare, and she has many, many awards and fellowships from Google, NSF, Meta. She has EECS Rising Stars and Data Science Rising Star Award, and she has uncountable numbers of newspaper articles, almost 1,000, 2/3 of that. New York Times, Washington Post, you name it. So I'm very pleased to have her talk today about her newer work, which I know her work on her PhD, but this one I don't, so I'm looking forward to that.
All right, thank you so much, Christian. Can everyone hear me? Great. Yeah, thank you for coming today. This is actually going to be a mix of my PhD work and my recent work, so apologies to those of you who have heard 60% of this before. So today we're going to be talking about inferring and simulating human behaviors for societal decision making. And we're going to begin with this premise that human behaviors are crucial to understand for societal decision making, but they're often quite difficult to observe. So for example, when you think about the pandemic and how we respond during a pandemic, we really care about this object called the contact network. And that's a network that describes contact between individuals. So nodes might be individuals or neighborhoods, and then edges represent contact between them. Maybe you sat at the same restaurant, or maybe you even live in the same house. And we care a lot about the structure of this network because infectious diseases like COVID spread through this network. And so the structure of this network then modulates both the spread of the disease and also how we respond. So for example, questions like how should we safely lock down, or how should we safely reopen? How should we distribute vaccines, especially when there might be a limited supply of them? Or how do we reduce disparities in infection rates? And where are those disparities even coming from? But it's not just pandemic response where we care about behaviors. There's a lot of domains where behaviors are really crucial to decision making. Another one is natural disasters. And so when you think about floods or earthquakes, you want to understand who is evacuating, who is not, who is making use of various resources like cooling centers in extreme heat. Another domain is transportation. So when you think about developing transportation infrastructure, like new bike lanes or a new subway line, you need to understand people's travel behaviors and how new interventions, like a new bike lane, is going to change, for example, their mode choice or levels of congestion. And then finally, it's not just about physical, but also about social behaviors and social decision making. For example, to tackle problems like political polarization, we need to understand how people are communicating with each other, through what channels, what is the structure of their social networks, how are they receiving information, and how are they then updating their opinions and their communications based on that. So in all of these domains, we care deeply about understanding human behavior, but human behaviors are hard to observe, and I'll give you a couple of reasons why. The first basic issue is just cost. And so if you want to do something like surveys, surveys are very costly. Both to conduct the survey, you have to recruit people, you have to pay the participants, you also have to find people to do that sort of recruitment. And so surveys are very costly. And that can limit how large of a sample size you can have, as well as how frequently you can conduct that survey. The second thing is that behaviors are highly heterogeneous, so different populations behave in different ways. And what this means for observation is that it's not just enough to get a sample. You need a large enough sample and a representative enough sample that you can slice it finely, and then you can see those different behaviors between different subgroups. So that's another challenge. A third challenge is that behaviors aren't static. So you can't just sample that behavior once. You need to sample it frequently enough so that you can capture rapid changes in behaviors over time. For example, at the beginning of the pandemic with large drops in contact and mobility. And so all of these issues compound on the issue of cost, because you can't just do one survey. You have to sample frequently, and you have to sample large enough. Another issue is privacy. So even if you could collect data on behaviors, do you want to release it or not? And sometimes you don't necessarily want to release that data for the reasons of individual privacy and protecting that privacy. And then finally, sometimes behaviors can't be observed because they literally have not happened. They are not observable. Maybe that's because they're behaviors in the future and you need to forecast them, or because they're counterfactual behaviors. So what if behaviors, for example, what if we hadn't locked down, or what if we had reopened in some other way? These behaviors are not directly observable. So what do we do? And so in my work, I take two approaches to this problem of behaviors being hard to observe, both machine learning approaches, but with different angles. The first one is, can we infer behaviors directly from novel data sources? And I'll explain what those are. And the second one is, can we simulate behaviors with generative AI models, like large language models or diffusion models? So the first approach is novel data sources. And by this, I'm referring to things like these large-scale passively collected data sources, like GPS from cell phones, or wearables, or social media, or search logs. So these are passively collected, constantly pinging, covering a large swath of the population. And so this addresses several of the challenges. First of all, it's a lot less costly now because of the passive collection. You don't need to go out and recruit participants. And then because it covers such a wide swath of the population, you're now able to sample that and slice that very fine so you can capture different behaviors from different people. And then finally, because they're constantly pinging, you can capture changes over time, including in real time. So for example, you see changes on social media or in people's search logs as their attitudes change. So these are all the advantages, but there's also these two remaining things. And in my recent work, I've been exploring simulations as a complementary method, especially, like I said, simulating behaviors with generative AI models. And so simulations can address the first three things. For example, they're a lot less costly as well, and you can also study heterogeneous and time-varying behaviors. But in particular, they can address problems that novel data sources might not be able to. So the first one is, when privacy is an issue, simulation gives you a chance to produce synthetic individual-level data while protecting individual-level privacy. And then simulations also enable us to imagine behaviors that cannot be observed. So specifically, these future counterfactual behaviors, with simulations, we can now generate them under different scenarios. Of course, the open question here is how realistic these simulations really are, and that's what a lot of my work addresses. And then finally, I'm not just interested in these behaviors just for themselves, but really about integrating them into decision-making models so that we can make better decisions. And here's some ways in which behaviors might allow us to make better decisions. First of all, if we can capture that sort of heterogeneity and differences across populations, we can now estimate risks and prioritize people who are most at risk. If you can also understand people's heterogeneous needs, then instead of having one-size-fits-all solutions, you can have policies that tailor to people's different needs, for example, different ways of communicating. Also, if you have real-time behaviors, you can also respond more in real time. So you can actually adapt as people's behaviors are changing. And then finally, very importantly, you can also evaluate policies better. So if, let's say, you enacted some sort of policy, like a new bike lane in transportation, if you have a good measure of behaviors, you now have your outcome variable. You can actually see, after you've enacted this policy, like a new bike lane, how did behaviors actually change, and get better causal estimates of the effects of your behaviors, of your policies. And so for all of these reasons, we care a lot about behaviors towards making better decisions. For today, I'm going to talk about these two approaches, starting with inferring behaviors from novel data sources, and we're going to focus on mobility networks and modeling COVID spread, and I'll cover some other examples briefly. And in the second half, we're going to talk about simulating behaviors with generative AI, focusing on a recent work in ACL, and then talking about a couple ongoing projects. So to begin, this work on mobility networks, this is work that was published in Nature, co-led with Emma Pearson and Peng-Wei Ko. And so, like I mentioned earlier, understanding this contact network is really crucial for understanding how COVID spreads and how to respond to it. For example, how do you reopen safely, or how do you reduce disparities? But the challenge is that we usually don't know the true contact network between individuals because we don't track who is coming into contact with whom. So if we don't know the true contact network, what can we do instead? And prior work has explored a number of alternatives. For example, maybe you can assume the graph structure, assume just uniform mixing within cities, for example. Or you can model contact at a much coarser granularity where you actually have the data, such as maybe airline networks. It might be easier to get that data. But these approaches miss important heterogeneity at local levels, because we know that even within cities, people don't mix uniformly. Another option is to add many parameters to an epidemiological model to make up for the fact that you don't have this contact network. Maybe you have transmission rates for every neighborhood. But the challenge with this approach is that the data to fit these models is very scarce, sometimes just daily cases for a whole city. So maybe you have 60 data points over 2 months. And so how do you fit models with many parameters on small data? They tend to overfit, and they struggle with generalization and identifiability. And so our solution in this work is instead to estimate fine-grained mobility networks directly from aggregated cell phone location data. So that's our novel data source here. It's location data from cell phones. And can we infer these fine-grained mobility networks that encode the real movements of people during the pandemic? And our premise was this. If you can successfully capture these real complex behaviors from data on the ground, then your model can actually be quite simple. So these mobility networks are going to capture much of the complexity of disease spread in terms of the heterogeneity across neighborhoods or long-tail distributions, and you can still accurately model the disease with a very simple epidemiological model. So the kind of data we're going to be using here, it's cell phone location data. In this case, we use data from SafeGraph. It's aggregated to the level of census block groups. So these are individual neighborhoods of around 600 to 3,000 people. I'm going to refer to these as CBGs in this talk. They also provide visit counts for points of interest, or POIs, and these are public locations such as restaurants and grocery stores. And SafeGraph has the original GPS pings, but they do pre-processing and aggregation in order to preserve privacy. And so you get, for example, so what we want in this work is we want the hourly visits of people to places. And so again, we have these POIs and these CBGs. So it turns into this bipartite network where you want to say, in every hour, how many people from each census block group visited each POI. And the reason we want this is then we can model the spread of COVID based on who was visiting where at the same time. The challenge, though, is that we don't actually have this network available in SafeGraph data. What we do have is, first of all, the hourly total number of visitors to each POI, so it's an hourly count. And then we also have the hourly total number of people coming out of each CBG who are out and about and visiting visiting POIs. And so this gives us the hourly granularity that we want, but it's not a network. Conveniently, from SafeGraph, we also have monthly estimates of where the POIs, where their visitors are coming from. And so this gives us a monthly network, but it's not hourly. And so our key idea in this work is that we can use an algorithm called iterative proportional fitting to infer these hourly CBG POI networks. And I'll explain now what that means. So for those of you who might have not heard of it, iterative proportional fitting, or IPF, it's this classic statistical algorithm, which you might know by other names like Sinkhorn's algorithm or biproportional fitting. And so the way that IPF works is you have an initial matrix, let's call it X, then you have the row marginals P, that's what you want the rows to sum up to, and then you have column marginals Q, that's what you want the columns to sum up to. And then IPF tries to solve what's called the matrix balancing problem. So that's saying, let me find diagonal matrices D0 and D1 such that by scaling X by D0 and D1, I can match both P and Q at the same time. So the rows sum up to what they should, and the columns sum up to what they should. And the way that IPF does this is iteratively. So on even iterations, we're going to adjust D0 so that we can match these row marginals P. And then on odd iterations, we're going to use the latest version of D0 and now adjust D1 to match the column marginals Q. And it's really simple. You just go back and forth, adjusting D0, adjusting D1, adjusting D0, and so on. Until hopefully, and I can tell you the convergence criteria if you're interested, hopefully these IPF iterations converge. And it's known that if these iterations converge, you will now get back this fitted matrix of the form D0 x D1 that matches both marginals at the same time. But it also has this nice property that it minimizes the KL divergence to the initial matrix, the Kullback-Leibler divergence. So you can basically see it as among all matrices that match both marginals, it maximizes similarity to the original one. And so our key idea is that we can use IPF to infer these CBG POI networks. It naturally fits in, so we have these hourly visitors from CBGs, the hourly visitors to POIs, and the initial matrix. And so these plug in to the marginals and the initial matrix, and we apply IPF to learn this fitted network, which basically this fitted network will represent our hourly network, and it will match both the hourly visitors to POIs and CBGs, but otherwise remain as similar as possible to the initial matrix, which is the monthly network. And in our follow-up work in ICML, which I'm just going to talk about very briefly, we brought in this problem to a general problem that appears in other settings as well. So we recognize this isn't just a safe graph data problem, but it actually appears in any setting where you have a dynamic network, and it's easier to observe its marginals than it is to observe its interiors. So for example, think of a subway system where maybe you have people coming into stations and people going out of stations, and you get the time-varying marginals there, but it's harder to know the paths that people are taking between stations. And so under this general problem, we ask when and why is IPF a reasonable estimator of the dynamic network in this setting? And our main result in this work is that we come up with a network model where we show that IPF actually recovers the maximum likelihood estimates of the parameters. So we define a setting under which IPF is quite justified for inferring a dynamic network from its marginals and time aggregated version. And so this basically allows practitioners, if they wanted to apply IPF in their settings as well, to see, does my setting match this network model and the assumptions of this model? And then if so, then you can apply it comfortably. And we have some additional results here when we test on other data sources, and we actually compare to ground truth hourly networks. But for now, I'm going to come back to the original application. So we applied IPF to infer CBG POI networks in 10 of the largest metropolitan areas in the US from March to May 2020 in the first wave of the pandemic. And I talked a bit about the theoretical properties of IPF, but one of its empirical properties is that it's very nice and lightweight because you can compute all of these scaling factors in parallel. And so we're able to do this at scale and infer these large-scale networks with 500,000 POIs, 57,000 CBGs, and 5.4 billion hourly edges. And we release these networks as a contribution unto themselves, and they've been downloaded by hundreds of researchers. In our work, we're now going to integrate these mobility networks into an epi model so we can model disease spread. And we use a standard compartmental design, so we assume that individuals can be in one of 4 disease states: susceptible, exposed, infectious, and removed. And the key to our model is that we maintain disease states for every CBG. So we keep track of how many people in each CBG are in each disease state, and then the mobility network controls how people come into contact. And I'll go over a toy example here to explain. Imagine we just have 2 CBGs, A and B, and everyone is susceptible for now, except one person in B who's infectious. And so let's say that infectious person and one of the susceptible people from CBG A, they visit the same POI at the same time. Now there's some chance that the infectious person infects the susceptible person, and let's say that happens. So now the susceptible person becomes exposed, meaning they are infected, but not yet infectious. And then both people go home, and after some time, the exposed person leaves their latent state and also becomes infectious. And we also model a second type of transmission that happens in your home CBG, which is separate from your POI visits. And let's say that happens here. So now we have 2 infected people in each CBG. And this is a simple example, but you can basically see from this example how the mobility network can instruct how people across CBGs come into contact with each other. You have disease states for each CBG, and this also enables you to model spread across CBGs. So the infection started in one, but now it's in multiple of them. Another thing I wanted to note is we can model POI-specific probabilities of infection. So it's not a constant rate, but we actually scale that depending on the POI's area in square feet. So larger areas, lower probability. Median dwell time, so that's basically if you visit, how long do you tend to stay? Number of infectious visitors, and current levels of mask wearing, which is daily and regional. And so altogether, our work can be described by this pipeline. So we start off with this aggregated location data from SafeGraph, and then we apply IPF to do the network inference, and that allows us to get these hourly CBG POI networks. And we combine that along with many other ingredients into our epidemiological model. The model will spit out some predictions, and we fit the model's free parameters by fitting it to actual reported case counts during the COVID pandemic. And then we use the fitted model to conduct all sorts of analyses, which I'll tell you about soon. But before we get there, I wanted to note that incorporating so much real-world data into our model means that the model can be very simple, which was the original premise. So it actually only has 3 free parameters, and these are just 3 numbers that are fixed over time. And despite that simplicity, we're able to fit all sorts of case curves during the first wave of the pandemic. So here the blue line is model predictions, the orange line is reported cases. And so our model is able to fit linear trajectories, like in Chicago, but also some harder curves, like in Philly or in New York. You see the cases going down. The fit certainly isn't perfect, but I'll remind you that the only thing that varies over time is the mobility networks, and the model's parameters are fixed. And so this shows the power of the mobility networks because they enable our simple model to fit all sorts of cases without many parameters.
How do you get the mask information, mask wearing?
Oh, that was reported, it was like externally reported by, I think, by surveys.
Sort of averaged by some area?
Yes, exactly. So we couldn't get it at the CBG level in that case. I believe that might have been at the county level, and it was daily. It varied daily, because mask wearing also changed over time.
Right.
Yeah, yeah.
How do you model the infections within your POGs? Do you assume there's homogeneous mixing there?
Yeah, so this is definitely a limitation of the SafeGraph data, where we can only see heterogeneous mixing within points of interest. That's because these are public locations. We can't see mixing that happens within people's homes. And so we basically modeled, I think we modeled it dependent on the density of the CBG. And so we could see how many people there were per square foot, and then there was just some additional scaling factor that was applied to that.
Another parameter for each PG, need to know the spread rate in it?
In that case, no, we just used one uniform parameter for all CBGs. So that's why we were able to get away with just 3 parameters. The 3 parameters specifically, for those of you who are interested, the first one was a scaling factor on all POI transmission rates, so just a single number that scaled that up and down. The second one was a scaling factor on CBG transmission rates, so again, just a single factor that scales everything up and down. And then the third thing was the initial proportion of people who are infected, because you have to infect some people in order to start a simulated infection.
These you assume are known, or you have to, because I mean you have sort of the rate at which you go between. So there's 3 rates between the 4 boxes. Aren't there already 3 more parameters?
There are 3. I'm not sure I understand. There are 3 parameters. Yeah.
Susceptible to
Yes.
exposed, that's one rate. You go from exposed to infected.
Oh, I
That's
see.
another rate.
Yeah.
You go from, and then you recover, that's another rate.
Yes, so that's actually a good point. So the thing that we mostly model is that transition from susceptible into exposed, because that's what happens when a susceptible person comes into contact with an infectious person. And so then they could transition into exposed if that infectious person in fact transmits to them. So that's the transition that we really focus on modeling. The transition from exposed to infectious, we just draw from a distribution based on prior work in terms of how long people tend to stay in the latent state. And then the other one as well. So we draw the transition from infectious to removed also based on prior work that had been estimated from epidemiological data. Yeah, thanks for the questions. All right, so now we have this fitted model. It's calibrated. What can we use it for? And so the first thing that we use it for is retrospective analyses. So you could basically think of our model. It's not really making forecasts, but it's making realistic simulations of who was infected where and when, down to the individual CBG, POI, and hour. And so this allows us to analyze disparities in risk. For example, which CBGs were the most at risk, or which types of POIs are riskier to visit. And then second, we can use the model for forward-facing, essentially scenario modeling. And so because our model takes in these series of interpretable inputs, so it has the mobility networks, it has the starting disease states, you can modify any of those inputs and run the model forward and get some sort of modeling of a scenario. For example, what if we reopened in a certain way? And so I'll show you 2 example use cases, but you can look at the paper for more. One of them is reopening. And so at this point, which was around mid-2020, people were quite interested in what's going to happen when we do reopen. And so we used our model to test a partial reopening strategy where we reopened all POIs, but we cap visits at POIs to some percentage of its maximum occupancy. And then we evaluate the reopening strategy based on 2 objectives. So on one hand, you would want maybe more visits because this serves as a proxy for the economy or consumer needs. But on the other hand, you want to minimize infections. And so, as you might expect, these are competing objectives. But the good news is that a small reduction in visits can lead to a large reduction in infections. For example, if you use a 20% occupancy cap, our model predicts that in Chicago, you would lose around 40% of visits compared to fully reopening, but you reduce predicted infections by 80%. And this strategy works well because it disproportionately reduces visits at POIs during their high-density, risky hours, but allows visits to return in other places. So you're essentially exploiting heterogeneity to get better decision-making. Another thing you can do is use the model to analyze health disparities. So what was remarkable was that our model correctly predicted socioeconomic disparities without demographic information, only based on mobility networks. And so it was well known at this point in the pandemic that lower income and more minority communities get infected at higher rates, but the question was why. And so we wanted to then understand, how is the model able to predict these disparities from the mobility networks alone? And we found that there were two mechanisms. So the first one is that lower income and less white CBGs were not able to reduce their mobility as much. And this was consistent across all cities. And this could be because they're disproportionately represented in essential jobs or less able to work from home. But this is why this heterogeneity matters. The second thing is, it's not just how often people go out, but where they go. And we found that people from lower income and less white CBGs were visiting POIs that were smaller and more crowded with longer wait times, even conditioned on the type of place that they were going to. So for example, on average, we found that one trip to the grocery store was 2 times riskier for someone from a lower income CBG compared to someone from a higher income CBG. So these findings reveal that mobility could be playing a substantial role in why we see these disparities, which also guides how policymakers respond to them. And so when we released this work, we were excited that the findings reached broad audiences. We received coverage from over 650 news outlets, including an interactive article in the New York Times. The work was also cited by various institutions and governments around the world. For example, here you can see one of the figures from our paper remade by the Office of the Prime Minister in Poland to be printed in a Polish newspaper. And we were also cited in 2 amicus briefs for the US Supreme Court and by other various institutions. But given all of this attention, we were excited, but we wanted to translate that into concrete decision support as the pandemic was still ongoing. And so to do this, we partnered with researchers at the University of Virginia who were advising the Virginia Department of Health on pandemic policies. And UVA had reached out to us about the department's need for data-driven tools to address reopening plans. And so together, we transformed our model into a new dashboard that allowed the Virginia Department of Health to assess thousands of different potential reopening plans, and they could analyze these trade-offs that our model could measure between visits and predicted infections. And it could do that over different tailored policies. So instead of opening everything or closing everything, you can decide how much mobility you want at different types of places. And so creating this dashboard required a substantial amount of effort. We met with the department repeatedly. We made new use cases for the model. We made this whole new dashboard so that they could interact with the model. And there's these interesting human-computer interaction questions that come up there of how do you communicate as much as you can while still being clear. And also we had to build a computational infrastructure to run the model at scale. And so in recognition of these efforts, this work won the Best Paper Award in KDD in the Applied Data Science track. So now I'm going to close up this first section on inferring from data sources and zoom out to the bigger picture about different types of data sources and what sort of behaviors you might be able to infer from them. So we've been talking about mobility data a lot so far, and I see this as a good example of data that tells you what people are doing, because it has the actions, right? They're already going to places. But in order to fully model people's behaviors and be able to predict them in particular, then you need to also understand how they got to those actions. What were they thinking along the way? Why did they or why did they not take an action? And so in order to understand those things, I find it quite useful to look at data sources like search logs or speeches or social media that are user-generated and often more textual, or sometimes these days, images or video. And so here's a selection of a few works I'm going to go over very quickly along these lines of more how do people feel about things. We have work in Nature Communications that's about analyzing vaccine uptake and hesitancy from search logs. So we basically show with large-scale web search logs, you can see when someone is trying to get the COVID vaccine, because they type in something like, where can I get a COVID vaccine? And then at scale, you can then analyze and compare vaccine holdouts versus people who are early adopters of the vaccine and understand their different vaccine concerns right from their search logs. Another work, which is more in the social science space, is we measured attitudes towards immigrants from 140 years of political speeches, and we basically charted out when the divergence between the two parties started, along with a lot of other results. And so the style of this work here is usually you're working with large-scale unstructured text data, and you have to come up with natural language processing techniques to squeeze the signal out of that data and put away the stuff that is not relevant. And so you often need methods that can be very precise, and you can find the signal that you need, and then you have to compare it ideally against some ground truth that can tell you that you've done a good job. And so finally, to end with some discussion, data sources are certainly imperfect, even though they're powerful. They don't cover all populations or all types of vaccine seeking in the search logs work. Privacy is always something you need to consider, and how to balance privacy with social benefits. And of course, the models themselves are imperfect and make simplifying assumptions. Even so, all of this together allows us to estimate behaviors at much finer granularities and derive important decision-making insights. So for example, in the work that I focused most on today, we infer these hourly mobility networks, which enable accurate fits of real COVID cases, and that allows us to study who was infected where and when, and inform both reopening and disparity policies. In the search logs work, which I didn't get to talk about as much today, we did train this vaccine intent classifier to identify vaccine intent. We got very high performance and also showed strong correlations with real CDC vaccination rates. But we showed that our search signals could precede the CDC vaccination rates by 1 to 2 weeks and also be 10 times as granular, which enables much more precise decision-making about where should I be placing, for example, vaccine sites or distributing vaccines. All right, with the remaining time, I'm going to switch over to this newer work, which is on simulating behaviors with generative AI. And I'm going to start with work that was published in ACL this year, which is led by my student Joseph, who's a PhD student in the EECS department. So to begin, surveys are very expensive. I don't know how many of you have run surveys. For example, a 10-minute RAND survey with 1,000 respondents is quoted for $37,000 and for adults, and then $72,000 for youth. And so a possible alternative that we've been exploring is, can you use large language models, or LLMs, to predict survey responses and essentially serve as synthetic respondents? And the goal here is not to replace human participants, but to augment surveys and make them more efficient. Here's a couple of examples. How? For example, if you can get strong predictions and know which questions you have good certainty for, you can reduce the total number of questions that need to be asked, reduce participant burden, reduce costs, and focus on the questions that you're less sure about. Another thing is maybe you can inform survey sampling design. So even a large survey still has a finite number of human samples, and you need to do stratified sampling and decide who to over or undersample from. And so if your synthetic respondents can give you a sense of variance within populations, you can use that to guide how much you sample from different groups. Another thing is maybe you had respondents fill out your survey, but there's always going to be missing answers. And so can you do simple imputation? A little more ambitious is, can you extrapolate to completely unseen individuals? Because again, your survey is only going to include some sample of people, and there will always be people that you weren't able to ask. And so this is sort of the hope for this field. The question is, how well does it work? So the way that we usually do this with LLMs is we'll set this up where we first condition the LLM on some individual or some group. For example, here we're going to condition it on people who live in the South in the US. And you can ask a question and then provide the answer as a way to condition the model. And then the second thing you do is then after the model's conditioned, you ask it a survey question. For example, here a question about whether women won't get jobs or promotions. And then the most popular way that people extract responses from the model is they then look at the LLM's next token probabilities. And so as you probably know, LLMs are trained on massive amounts of data to do next token prediction. And so you can extract the log probabilities from the final layer of the model to see what is the probability of each answer option in terms of A, B, C, D, and E corresponding to the survey question. So prior work has explored this, but they found that there's challenge in steering the models towards the opinions of certain groups. And so sometimes if you don't provide any group that they're supposed to specify, they lean more towards liberal and more wealthy groups. If you do provide the group they're supposed to follow, that steering still doesn't quite work. However, prior work has mostly used prompt engineering for this problem. And so in our work, we asked, how much better can you do if you fine-tune LLMs directly on response distributions collected from survey data? And in particular, how far can that fine-tuning then generalize to unseen questions? Because this is how the survey respondents, how these synthetic respondents would be used in the real world. And so what we do is we construct this large-scale fine-tuning data set in the format of group and question. And so you have a group, you have a question, and then you have the response distribution of that group to that question. And then you directly fine-tune the model's next token probabilities to match that distribution as well as possible. And there's several advantages, we think, to fine-tuning the model in this way compared to what it would have naturally learned from pre-training data on the internet. The first thing is this construction explicitly pairs the group and the question. And so now you explicitly say this is the person's identity and this is how they feel. And you might be able to infer that from the internet, but oftentimes you don't have the opinions and the identity so explicitly described. And when you are able to figure it out, it's probably non-representative. Another thing you can do is because we're directly fine-tuning on distributions, the model can learn variation within populations. And one of their failure modes is that they often assume too little variance within populations and assume that they're all the same. And so now we're directly teaching it the variance. And the third thing is that, of course, the internet is big, but it's not representative. So certain groups are oversampled, some groups are underrepresented. And so through this careful survey design and the high quality of the surveys that we're using for fine-tuning, we get those representative samples. And so we set this up with our data set, which we call SubPop, and we have 53 waves from the American Trends Panel, which is a US representative survey conducted by Pew Research Center. And we have 53 waves, and then we have 22 different demographic groups that we're going to fine-tune on. Altogether, this comes out to be around 70K group question pairs. And importantly, we have an equal number of data points for each group. And like I mentioned, we care a lot about generalization in this work, because if you were a survey researcher and you wanted to use one of these models, it's not going to be on a question that Pew already asked. It's going to be on a new question. And so we test, first of all, unseen waves of American Trends Panel. And the way that ATP works is that it's conducted in waves, and every wave is a time point and a selection of a few topics, like maybe about gun control or maybe about phones. And so when you test on unseen waves, you have new time points coming out and also a few new topics coming out. And so that's how you can think about the sort of out-of-distribution nature of unseen waves. We also consider unseen groups. So we fine-tune on 22 demographic groups, but then we also test on groups that weren't even seen during fine-tuning. And then we go even further and we say, can we generalize the unseen survey families? So the general social survey is conducted by NORC at UChicago. So it's still US representative, but it has a different panel of participants that they're sampling from. It has different survey sampling strategies and so on. And so we test generalization to unseen survey families. And then the evaluation metric that we use is we have the human distribution and we have the LLM distribution. And we use the one-dimensional Wasserstein distance to quantify the distance between the two. You don't have to read the math too carefully, but basically understand that it measures the cost of shifting the probability distribution. And what's nice about Wasserstein is that instead of just treating this as categorical, you can actually map the answers to ordinal values and measure the distance from, for example, strongly agree to strongly disagree is a larger cost than moving from strongly agree to agree. And so when we evaluate the results, we're going to compare to baselines, which are the prompt engineering methods from before. And then we also have a lower bound, which is the best performance that you could expect. And the reason we have this lower bound is because the human samples we have are still not ground truth. It's still a sample from the human population in the US. And so we measure the lower bound of human agreement with each other by doing bootstrap sampling of the human sample. And so what we find is large improvements from fine-tuning to these unseen questions. First of all, we see large improvements to unseen ATP waves, 41 to 48% improvement. But this also generalizes to the GSS. So the General Social Survey conducted by a completely different organization, we still see a similar scale of improvements, 42 to 50%. Furthermore, we see that the improvement is large and consistent across subpopulations. So we fine-tuned on 22 subpopulations, and here we're testing them on unseen questions, and we see this large improvement from 38 to 54%. And we attribute this in part to the fact that our fine-tuning data set pays an equal number of data points to every group. And this addresses questions of fairness and bias that have come up in prior work, where certain groups are better or less well simulated. And finally, we see for unseen populations even large improvements, comparable improvements of 38 to 55%. For example, none of these age groups were seen during fine-tuning, but the model still does a much better job at predicting their answers at test time. And you might be wondering, how is this possible? And we have a couple of hypotheses. The first one is, through fine-tuning, you just bring the model closer to human distributions in general, before you even think about specifying for a specific subpopulation. Just a general human human distribution. For example, these models, like I said before, didn't have enough variance, and now they learn a general amount of variance. The second thing is, even though there are some groups that are unseen, they might have other groups that were seen within the same type of variable. So what I mean by that is, for example, less than high school education and college grad were seen during fine-tuning, but then high school graduate was unseen. And so you might be able to interpolate between the groups that were actually seen. And then finally, for the completely unseen demographics, like age, where none of the age groups were included, large language models still have just a basic natural language understanding. And that's one of the reasons why they're so powerful in this setting, where you could show it something unseen, and even if it hasn't seen that before during fine-tuning, it might have had a natural language understanding of what ages are and how different age groups relate to other groups, for example, liberal or conservative. So in conclusion, in this work, we curate this new data set, SubPop. It's publicly released online. If you want to use it, you can download it from Hugging Face. And we show that fine-tuning reduces the alignment gap between LLM and human responses by 38 to 54%, consistent over subpopulations, and it generalizes to unseen subpopulations and survey waves and even survey families. And we have some additional experiments that I can tell you about, too. So I focused a lot on public opinions and surveys, but there's other types of behaviors that you can also simulate. For example, in our past work, which was also published this year, we explored, can large language models generate realistic social networks? So you essentially instantiate every LLM with a person's description, and then you have them talk to each other and see, can you formulate realistic social networks within each other? And we measure different properties like density and clustering and community structure, long-tail degree distribution. Basically, what we find is that they actually can match a lot of the structural properties. But one interesting result is across companies, so across OpenAI, across Google, and across Meta, we see that they consistently overestimate political homophily and polarization. So they essentially refuse to make Republicans and Democrats friends, sometimes to the extent that the network fractures into two disconnected components. And this would be quite bad if you then try to use these synthetic networks to simulate, for example, disease spread, since there's no way for the disease to jump from one component to another. We also know in social networks that they always have a giant connected component consisting of 90% of nodes or more. So this is just qualitatively incorrect. And so this sort of political bias is really important to study, and what that will actually mean for downstream simulations built on LLM synthetic data. Another thing that we've explored is, can LLMs simulate users in open-ended contexts? So for example, we ran this study at Microsoft called ChatBench, and we were trying to target this problem that a lot of generative AI models like ChatGPT, they're out there in the world now talking to users all the time, but the way that we test models is oftentimes still very static. So we test them on benchmarks like MMLU, which are curated from large-scale textbook questions. You show them a bunch of questions, you see whether it can select the right answer or not. And so we wanted to understand what happens when you incorporate a human into that interaction. And so instead of asking those static questions in the original benchmark way, we actually ran large-scale human experiments where we brought in users to ask the same MMLU questions, but in an interactive format as a conversation. And we basically show, even controlling on the same MMLU questions, the evaluation conclusions change a lot when you bring in these humans. And so the original benchmark results were not predictive of human AI outcomes on the same set of questions. But one silver lining is, could you actually train an LLM to simulate a user? And we basically do that on our data, and we show that for unseen questions, that simulator, when it talks to the original AI model, does a much better job at predicting the human AI outcome than the original benchmark did. And so can you do this at scale? Can you create interactive evaluations by simulating users to evaluate AI models in more realistic ways and build better AI? Okay, finally, with the remaining time I have, I want to come back to mobility data. I feel like this sort of brings it full circle. We talked a lot about mobility data at the beginning of this talk in terms of inferring behaviors from mobility data, but now putting on our simulation hat, can we actually instead generate mobility behaviors? So previously, we talked about inferring mobility networks from CBGs, which are these neighborhoods of 600 to 3,000 people, into POIs. And so this was really useful because we can model the spread of COVID COVID, but it's still quite aggregated, right? We're still at 600 to 3,000 people. Now we're interested in generating individual level mobility trajectories. For example, a trajectory is like a sequence. Think of like this person, maybe they started at home, then they went to get coffee, then they went to the office, and then they went to the bank maybe, and then they went back home. And so it's this time-stamped sequence of visits with a lot of widespread applications, for example, in public health, for individual level modeling, for urban planning, for transportation, for measuring social inequality and segregation between groups. And we have an opportunity now, actually, at Berkeley, with access to device-level data, where we're training diffusion models to generate synthetic mobility trajectories, and then we're going to adapt that to various target populations to generate mobility trajectories for any synthetic population. So if you're interested, talk to me about that. I'm going to briefly plug my final project now. This is new work with, oh, sorry, I forgot to mention. This work is led by my students Jessie Lee and Zhiqing Hong. New work with Jonathan Stray at the Center for Human Compatible AI, or CHAI. And here we're interested in this foundation that my student Joseph built with a previous work, Subpop, of synthetic respondents, but now applying it towards this really important AI question. And the question is, how do we build politically neutral AI? And our framework is, given a controversial question, neutral AI should produce a response that maximizes approval from people across the political spectrum. Imagine a question like, should abortion be legal? So imagine we have two groups, just to simplify things, A and B. And so when you plot approval over these two axes, you would imagine that there's some stuff in the bottom right corner where only A approves because it's very pro-A. And then there's some stuff in the upper left corner where B approves because it's very pro-B. But then the question is, what does that frontier look like between those? Can we map that out? And then can we find the sort of maximum approval point where we can balance between two groups and try to get people to the same table again? And so the first part of this project is finding the maximum approval curve through surveys. We're in this stage right now, showing participants hypothetical AI responses to a controversial question so we can map out the shape of this curve. But then the next two steps, which you might have guessed, the second thing is, can we automate this process using LLM synthetic respondents in a very similar way to what we did in Subpop? You condition the person on their position and maybe demographics, and then predict whether they would approve an LLM response or not. And then you do this at scale over many different controversial questions. And the hope is that we can build these open source tools to evaluate whether an AI model is neutral or not, which is of a lot of importance to our government and to our society. And so in summary, this work that I've talked about today, the end goal is always improving high-stakes decisions, making society better. But the problem before we can get there is that behaviors are hard to observe. And so to do this, we apply two different types of approaches, one of them inferring behaviors from data, and the second simulating behaviors with generative AI. So with that, thank you so much for listening, and I'll take some questions.
Wait.
In terms of tracking locations of people for the work, did you think about using indoor location tracking, using, for example, Wi-Fi signature signals? Then you could model the movement inside the building, let's say soda hall or whatever, and have a much more accurate, perhaps more granular.
Yeah, that's a great question. I haven't had access to that kind of data before, but I do think, not being able to see what's happening inside of buildings is quite a limitation, especially because a lot of these infectious diseases spread more indoors than outdoors. So knowing if you're in the same room or not. I have been talking to some people at hospitals where there's actually better data on this, of thinking about healthcare-acquired infections, HAIs. And there we do have within building measures of where the healthcare workers were and then where the patients were. And so with that, you could actually construct indoor mobility networks. But I think that is a good point.
Serina, thanks for the great talk. On the fine-tuning stuff, you started out by saying why surveys are bad, but then, of course, you use surveys to get the data to do the fine-tuning. So do you think about or understand how much data you need in order to build a reliable model? And if synthetic, you could leverage what you do have by generating synthetic data, kind of amplify and minimize the need for surveys. Is that something you work on?
Yeah, I mean, I wouldn't say surveys are bad. I think they are sort of the gold standard that we have right now, but they're hard. Like, they're hard to collect that much data. And so when we do have them, it's a good thing to try to validate against. I think the goal here eventually is what you're saying. I think in terms of how much data do you actually need to do a good job, we have plots in our model basically showing how performance scales with the amount of fine-tuning that you're providing. And we divided the data set into 25%, 50%, 70%, and then 100%. And you show, as you might expect, the majority of the gain is in the first 25%. You do continue to see small improvements afterwards, but I do think there's hope even for smaller data settings.
And can synthetic data techniques help?
Yeah, I think so. You mean in terms of like increasing the effective sample size or something?
Generating maybe from a small set of real survey data, generate a bunch of synthetic data with the same
I think so, yeah. I think there's at least two approaches. You can take a small amount of survey data and use it either for fine-tuning or in-context examples, and then use that to condition your synthetic respondents, and then do that at scale. So you could basically augment your data set and try to get more samples. Another thing you could explore is something like prediction-powered inference, like PPI, where you basically you have some sort of classifier that has predictions, and you have a lot of those predictions, and then you have a small set of ground truth, and you use the ground truth to basically correct the classifier, and then you apply the classifier at scale to your full data with those corrections.
Right.
Yeah.
Thanks.
Any question?
Thank you for the prepresentation. My question is on your ongoing work for the politically neutral AI. I'm just curious if you said the neutrality definition is maximum agreement among all different kinds of groups.
Yeah.
So if the agreement changes over time, or there has been a really big event where the crowd agreement shifts like immediately, then would that means it requires constant like fine-tuning and updates to produce a truly neutral political AI that sustain over time?
Yeah, I think that's a great question, and I think it's certainly true that public opinions change over time. We actually have current work right now on trying to model the evolution of public opinions. I think that's one reason why these sort of LLM synthetic respondents are potentially so powerful, which is that you can integrate real-time information as you go. So instead of just fine-tuning it once, maybe in 2023, and just leaving it at that, you can integrate more survey information as it comes in, but also like social media. You can integrate news articles, you can integrate economic indicators, and so you can allow that model to update in real time as people are talking online, and you can see that opinion start to shift. And so as an empirical question, yes, I think you could actually update these synthetic respondents so that you update the approval frontier as it changes.
Thank you.
Yeah.
Thank you for the talk. I'm wondering, for your work on the individual user simulations, like what are the use cases for that, and is that something you're still doing, or is anyone else still doing that?
Yeah, yes, I am very interested in this user simulation stuff still. I think the primary goal for us was evaluation in this case. So it's basically saying, right now, the way that we often evaluate generative AI is very static. So you show it some sort of textbook question, and you see whether it gets the right answer or not. So can we convert that instead to user AI interaction, where the user asks the AI a question, and then the AI tries to respond, and then the user maybe corrects them, or asks a follow-up question that is contextual, and the AI has to be able to understand all of that, and then you judge the interaction in that space. And so the goal is basically, can we evaluate AI in a more realistic way, ideally with real users, but it's hard for that to scale. And so the goal is to get some real users and then train a simulator on that so that you can actually scale it to any sort of AI model and any sort of task. So yeah, it is still something I'm interested in. I think that's the primary use case of learning how to evaluate, but another use case could be figuring out how to personalize models too. So if you want AI models to be able to learn from user feedback and be able to update, maybe Serina likes longer emails, or maybe she wants to have more commas in her sentences. If it can see how I update, if it can see how I edit its responses, then it can learn from that sort of in the wild feedback to give me better responses in the future. And so simulators might be able to help with that as well.
I also have a question concerning when you were starting with this groups of people where you only had sort of aggregated data, and now you're trying to actually find sort of by simulating personal data.
Yes. Yeah.
are you worried about privacy there? I mean, they were aggregated for a reason. We know that if I start with something strange and now I give you my social security number and my birth date and my zip code and something else, you can infer my social security number. Now you have this data, you add to it your simulation. So is it maybe that these data are private but not really differential private, and you could actually therefore use your methods to be really creepy on privacy?
Yeah, I think it's a great question. I mean, I think now that we are exploring more individual stuff, it's something I want to explore too. That's something I've been thinking about in the generating synthetic mobility trajectory setting, because that is very individual. And people have shown, for example, even if it's a de-identified mobility trajectory from just a few points, you can figure out like a home location, a work location, and maybe one more. You can actually identify a person from a data set. And so when we generate these sort of synthetic trajectories, especially if we're going to release anything, we're going to try to do that sort of check to make sure it can't be mapped back to anybody in the real world. The other thing that we're going to do is when we generate these synthetic trajectories, it's actually going to be for synthetic individuals. And so we're going to start with synthetic populations that already don't map one-to-one to real people, but it's sort of like a made-up person with certain attributes, and then we're going to add a synthetic mobility trajectory to that. And so I think there's less of a risk there because we're generating synthetic trajectories for synthetic people. But I think you should still be careful not to create anything that can be mapped to the original data set. I do think it's an interesting problem that I do want to work on more. All right.
Do we have one final closing question? Somebody wants to ask one last question. Did somebody say yes or not?
Okay. All right, thank you so much.
Thank you so much.